Hello ladies and gentlemen, welcome back. Today I'm going to be going over what I call the basic functions of the ALU, and by all that I mean is I'm going to do the OR and NOT and the shifts, because these are much easier to understand. They don't have near as many logic gates as both the comparator and the adder. So I've gone ahead and jumped in game already so that we can just have a quick look at these. Not planning on this being a long video because I don't think you will have any trouble understanding what's going on. So let me go ahead and click on the OR operator, and all that's doing once again is just letting it be enabled onto the end so we can go look at our result. So we see that I have 2 bytes and the OR is just taking one piece from both of the bytes. So if I were to put on, we see that they just mirror each other, is all I want to notice. So the 0 byte is up here, or the 0 bit is on top for both, and the 7 is on the bottom. So it is comparing the same bits for each byte. So we know that an OR gate is on if one or the other is true, or both. So for this, all we're doing, we just have the 0 bit on. Obviously we take one off, it still stays on because of the fact that we only need one to be on. We take the other one off, it turns off as well, and we can do this for all of them no matter what we're doing. I don't think there's really nothing else to go over here. That's pretty much all the OR function is. The AND function is pretty similar. If you recall that you need both inputs to be on for it. So just having a 0 on, we see does not turn on this gate right here. But if I turn it on for the other one, we do get out the input. So let me just wind up here. Let me turn on the AND operation. So we see that once again we have that 0 bit that's turned on like we expect it to be. And if we turn on other bits, nothing happens because we need both of them to be on. But if we mirror that with both bytes, we'll see it gets turned on. And so the usefulness for this is obviously if you want to see if both bytes have a specific bit that are on, you know, like they might both have a 4 on, but then they could be different somewhere. Like you could have a byte like this, and when you AND them together, obviously you see the 4 and the 4 are both on, the 7 and 7 are both on, and so this is what they share in common, essentially. Going into the NOT gate only takes input from one byte and then NOTs it, so just negates it. So we see up here that our byte A, we have, let's see, are we taking byte A or byte B? I feel like something's... What am I doing? One, two, three, four, 5. Ah, that's what's wrong. Sorry. Okay, so now it's correct. I was very confused at what was broken for a minute. So we have byte A knotted, and so once again we can see that right here 2 and 3 are turned on, and then 5 is turned on because they are off in the byte itself. So if you want your entire input on, all of them have to be off. You know, like I said, it's just knotting them together. There's nothing really terribly difficult to understand here. So now let's go on to the shift operations. So you have your shift left and your shift right. And so if you've ever done any binary math, essentially shifting left is like you're multiplying it by 2 because you're just kind of, what's the best way? So you could either be, in binary you're multiplying it by 2, or you're just adding a 0 onto the right side of it and you're just bumping everything 1 up to the left. So let me go ahead and click that shift left. So right now we're all at zeros. But notice what happens if I turn on the 0 byte or 0 bit of byte A. I'm going to have to get better at that. So we see that actually the second bit gets turned on, and that's because we bumped it up 1. And so we can continue doing this where we're just bumping it up so that everything is just shifted 1 to the left. You know, instead of it being at bit 2 becomes bit 3, bit 3 becomes bit 4, just on and on. And then this bit actually kind of gets, it's not really connected to anything because it's off of the chart. But what you can actually do with this is it will go out to a flag that will say you've like over that you're over the byte that you have. Because if we shift bit 7 up to bit 8, well, there is no bit 8. We're bit 0 through 7, but we have what's called an overflow, and we can send that out to a flag to let our control unit know that an overflow occurred. And so shifting right is very much the same thing. Let me go ahead and click on it. So now we're just shifting everything down 1 or to the right 1, which would be the same as dividing by 2 in binary. So we see, let's just start off with one example. So if we turn on bit 7, it becomes bit 6, and likewise. And the same as how the other, for shifting left, you could fall off the edge on the large side. For this, you can actually fall off the edge on the low side, where you can shift below, which becomes an underflow, and that will once again be sent out to another flag. I may not have that. Oh, I just turned it on wrong. Never mind. And so this is actually our underflow bit right here, and because that would be, instead of being bit 0 would become bit -1, so we'd have to send it out to a flag, and that would have let the control unit know that we have underflowed our byte, because there is nothing on our byte that can hold that. Well, that's pretty much it. I think I may have actually gone in a little more in more depth than I meant to, because once again, I think these are pretty easy, and I don't think you guys will have any problem understanding them. In the next video, I'll probably go over the comparator, just all of its functions, how the gates work together. It is pretty easy once you get a hang of it, because there's a decent amount of gates here, but it's just repeated over and over. So you see, like, you have like a little square right here, and then you just jump over and you have the exact same square just connected to the previous one. And the adder circuit is very much the same way. Well, I hope to see you guys next time. Bye.